Hi, everyone. Thank you so much for joining us today. We made it through the snowiest and probably the coldest week we've had all year. And we're excited to be kicking off Engineers Week with this Tech Talk today. So I hope you're all excited. And my name is Abby Heitzman. I am the Vice President of External Affairs for the SWE Central Indiana section. And today we have a very exciting speaker. Do a quick introduction and then we'll get started. So George Heitzman is our speaker today. He's a PE and the Assistant Director of the New York's Division of Environmental Remediation. He's got more than 35 years of experience and in the investigation and remediation of hazardous waste sites, with the emphasis on brownfield sites, manufactured gas plants, sediment remediation, and most recently emerging contaminants. He served as the incident commander for the state's initial response team of PFOA contamination in Hoosick Falls, where treatment systems were installed on public water supply and more than 800 homes, and directed the investigation of firefighting foam releases from the Stewart Air National Guard Base in Newburgh, where the water supply for more than 29,000 residents was impacted. He holds a BS in chemical engineering and a master's in economics from Rensselaer Polytechnic Institute and is a licensed professional engineer in New York State. And I know he's got a lot to share with us, so we'll jump right in and get started.
Thanks, Abby. So there's two parts to the presentation today. One is how we address chlorinated solvents, which has sort of become the bread and butter of the environmental industry since I started my career, for the last probably 30 some odd years. And chlorinated solvents are a good example of some of the engineering technologies that we use to treat contamination that's been released to the environment, as well as some of the investigation techniques that we use. So I think it's a good sort of primer on the existing technologies we have available to us. And then the second half is talking about the new generation of environmental contaminants that have really become apparent in the last 5 years. And those are the fluorinated compounds. So with that, I don't have a whole lot of chemistry slides, but I'm going to start you off with one. When we talk about chlorinated solvents, there's sort of the big three, and those are the chemicals that are at the bottom of the screen here. And they're all sort of related. They're two carbons. In this case, this is tetrachloroethylene, where the carbons are fully saturated with chlorine. We have trichloroethylene, where 3 of the 4 carbons are amended with chlorine. These both have double bonds. That's why they're called ethylene. And then we have trichloroethane, which does not have the double bond, but one side of the carbon chain is fully saturated with chlorines. These are sort of the most common contaminants that we see. They were very useful industrial degreasers. They're very good at removing and dissolving nonpolar chemicals. And for that reason, they were the go-to chemical for use in dry cleaners. They're also very good chemical solvents for manufacturing other chemicals, like dissolves like, if you remember your organic chemistry. So if you were manufacturing an organic chemical, you might have used one of these chlorinated solvents in manufacturing. They're very good at cleaning automotive parts. So every body shop, every engine repair shop typically use these chlorinated solvents when they were cleaning their parts. So one of the reasons they were so useful is that they were non-flammable. The chlorine to hydrogen bond is pretty tight. As a result, if there was any open flames, it would not break that bond. The chemical would not catch on fire. And it was also useful because it was soluble in water. When you were done degreasing something, you could hose it down with water, the solvent would come off, the grease would come off, and you would have a nice clean part for painting or whatever else you were doing as part of your operation. So the problematic properties of these chemicals, the big one is that they are denser than water. Perchloroethylene, the 4-chlorine chemical, has a density of about 1.9 in relation to water. Trichloroethylene about 1.6. So these chemicals sink when they're released to the environment, and they pass right through the water column. Unlike a petroleum that floats on top, these chemicals will sink right through, and you'll see later how that causes problems for us when we go to clean them up. They're also volatile, so when they're released, they can travel through the subsurface, they can vaporize and enter people's homes, and you'll see some good examples of that. And then that solubility in water, that was an asset, in their use in a plant, is also a problem when they're released in the environment, because as they're sinking through the water column, they're also dissolving, and they're migrating with the groundwater as it moves through the subsurface. And then in terms of health effects, there's pretty well documented health effects. In terms of the nervous system, it contributes to Parkinson's disease. And the big one is that it causes both liver and kidney cancer. Liver and kidneys are the primary filters in the body. Chemicals that are introduced to the body, typically they'll go after the liver and kidneys because those are the filters. So there's a couple case studies I'm going to show you. They're all sort of compiled into one example. But typically, these are the sites that we deal with, these abandoned dry cleaners. In this case, this is one in suburban Albany where I work and we live. There's a house nearby, which becomes important when you talk about exposures. This looks like a 2-family house. Looks like there's 2 doors in the front. So 2 families that are potentially affected by the contamination at this site. But in addition to abandoned dry cleaners, we also have to look at active dry cleaners. These cleaners may have been operating for 40, 50 years. They're often located in strip malls. I'll bet you guys can all think of an example of that. Here we've got a Domino's pizzeria that's located next to this one. As you can imagine, Domino's uses ovens to cook their pizza. They have ventilation systems to clear the pizza fumes out. And those ventilation systems become important when they draw air in, either from the wall, through the cracks between the dry cleaner and the pizza shop, or under the slab, or through whatever vent the dry cleaner has, or the soil for whatever may have been released over time from the dry cleaner. So interesting in this picture, you may not be able to see it, but there's a nail salon right next to the dry cleaner. So now you've got another source of primarily non-chlorinated solvents. The nail salons typically use toluene, but if you've ever walked into one, not that I have, but you can imagine the vapors that are coming out of the nail salon. So we deal with both abandoned and active dry cleaners that have a history of chemical use. So how are the chemicals released to the environment? Well, when a dry cleaning machine will use a small amount of solvent, but in it absorbing all the grease and the stains from the garments becomes fouled. And at some point, it becomes almost sludge-like. And the standard practice for a long time was to simply take the sludge out or take the filters out and put them in the dumpster that was out back. These dumpsters are not watertight. This is I went to the web and picked out the ugliest example of a dumpster I could find. It looks like the filter has been placed on top of this one and all the stuff is draining out of it. But even if it was placed inside, these things are not watertight. They fill up with water. There's holes in the bottom to drain them, and you get situations like this. So when we investigate dry cleaners, the back door or the location of the dumpster is one of the first places that we look. Some dry cleaners actually hooked up drains to their dry cleaning machine. The pipe you see here goes to a drain either inside the facility, maybe in the basement of the facility, or out the back door. This could be a drain in a parking lot, a storm drain. This is a nice floor drain inside a manufacturing facility. this may have handled food. This is just an example, but we see things like this in dry cleaners as well. As I say, on the ground floor, in the back, or in the basement where the dry cleaning machines are. And this is another place that we start looking when we start cleaning these things up. And then where do these drains go? Well, in a lot of places that are not on sewers, they go to a structure like this, which is a dry well. You know, the pipe comes in from the facility or from that drain that we saw in the parking lot. Goes to a series of perforated drums that are packed in gravel. And the first one fills up, and then it overflows into the second one, and so on into the third one. And so these dry wells are really ground zero for a lot of the solvent contamination. And then finally, even if it's piped to the sewer, you may have decaying infrastructure like this rusted cast iron sewer pipe. And you can see the hole, and you can see the water and the sheen on the water that's come out of it. So, you know, even if there's no dry wells, we have to look along the sewer pipe alignment to see where this stuff may have leaked out. And then finally, the lint. You know, dry cleaning machines, just like your dryer at home, collect lint over time. And I had thought I had seen it all. And we went to investigate a dry cleaner one day, and there was this huge pile of lint out in the back. This figure, obviously, I took from the internet, from Dad's dryer vent cleaning company. But the workers at the dry cleaning facility would take the lint out because people would leave jewelry in their pockets or would get snagged on a sweater that had to be dry cleaned. And they would just spread the lint out in the back and look for jewelry that came along with the dry cleaner and got stuck in the lint trap. And then, of course, they would just leave the lint stuck out back in a big pile. And the stuff is not soaked with solvent, but there's enough solvent in there that when the rain comes, it's soluble and it washes out of the lint and enters the ground. So, you know, a couple different mechanisms for how dry cleaning solvents got released over time. And this is just talking about dry cleaners. You know, we have all the industrial operations that discharge much larger quantities, but when you run a dry cleaner for 40 or 50 years, it builds up over time and creates a problem. So now let's look at how, once it's released, how it can affect people. And so on the left-hand side, this is an industrial scenario with an above ground storage tank that leaked, but the principle is the same for dry cleaning solvents that may have leaked. And again, because the solvents are heavier than water, they sink right down, and we call this the chimney effect because it's, you know, a column through the soil that is relatively small, gets below the water table, keeps sinking until it reaches this, what's called an aquiclude, which is some kind of confining layer in the geology that stops the downward flow. You know, this could be typically as a clay, it could be bedrock, as long as that bedrock is competent. And then the separate phase material, the pure solvent, travels along the surface of the confining layer. And depending on how that surface is sloped or shaped, that will affect how it migrates, you know, which way it goes, essentially. And then in the meantime, because this stuff is soluble, it will dissolve its components into the water table. And that's what this figure, you know, the dark red or pink, high concentrations, lower concentrations, as it moves with the groundwater flow away from this chimney of separate phase material. Because it's volatile, you see as it passes through the soil column, it will vaporize. And depending on how close a house is and what's going on inside that house, those vapors can now enter through the basement slab. This first house is a slab on grade. The second house has a full basement, and basements are notorious for allowing vapors to enter the house. And each of these houses may have wells. You know, that's what the blue line indicates. They may not be on municipal water. They may have supply wells. and they may be tapping into what is a contaminated groundwater source. So some interesting factors that affect the vapor, what the heating and ventilation system is in the house, whether it requires makeup air that may be drawn in through a basement slab, which way the wind is going. This can actually create a sort of a Venturi effect where it's sucking air as it passes over an open chimney, and that air has to come in from somewhere else and may come in from the basement. Getting back to the industrial building on the left-hand side, they show the elevator. The elevator, as it goes up and down, creates sort of an air pumping effect where as it goes up, it draws air in from the shaft that's below grade, and elevators are actually a significant route of migration for vapors to get into a building, as well as the HVAC system that may be operating within that building. So, a couple mechanisms for how vapor can enter a building, and certainly how groundwater may be affected and people may be exposed to it. So this is one of New York's most notorious chlorinated solvent sites. This is the Northrop Grumman Naval Weapons Facility. Two facilities, actually. Grumman is the topmost one, indicated by the sort of brown shading, and then the Naval Weapons site is right next to it in the blue shading. They mostly made Hellcat fighters during World War II. That's kind of how Grumman got started with large-scale production. The Navy was making various sort of weapons products, but in all of those, they use these chlorinated solvents as part of their metal processing operation for painting, degreasing prior to painting, and so on. This has created a plume in Long Island's aquifer that is about 4.5 miles, 4.25 miles long, and about 2 miles wide. This has affected several public water supplies that draw their water from this very productive aquifer. It's a very nice sand and gravel aquifer that was produced when the glaciers came by and left a nice moraine of sand and gravel. And then all these little roads you see are people. This is a residential area right next to this formerly industrial area. And so vapor intrusion is a concern with all the people living over this plume, as well as the water supply. So I talked about vapor intrusion into basements, and here's how we investigate that. What you're seeing on the right is a canister that arrives with a vacuum in it. We drill a hole through the basement floor, and we put the probe through the floor and then seal it. And then the valve on this vacuum canister is calibrated so that it draws air very slowly in over typically 8 hours. And we get a nice 8-hour sample of what's going on beneath the slab. And then similarly, we will put a canister in the living space of that home. And we try to put it in the breathing height, roughly 5 or 6 feet above the ground, where people would be breathing the air to get a representation of what they might be breathing. And through this, we can determine A, if what is beneath the slab is contaminated, and B, how much of it is reaching the living spaces in the first floor typically. Because of all of those factors that I had talked about that might draw air up into the basement and then into the upper floors. We often see that there are very high levels beneath the slab and that there are levels in the house that are unacceptable, and I'll show you how we deal with that. But we occasionally see that the levels in the upstairs are actually higher than what they are in the basement. And that points to indoor sources of contamination. And one of the first questions that we ask people when we sample is, have you had clothes dry cleaned recently? And it raises the question, and typically where we see higher levels in the house, the answer is yes. And it raises the issue of how people handle their dry cleaning when they pick it up from the store. You know, they come in these nice plastic bags. And what a lot of people do is they bring them home in the plastic bag. They bring the bag into their bedroom. They strip the bag off and put it in the garbage, and they hang their clothes in their closet. And a couple hours later, they go in there and sleep for 8 hours. Um, this is not a good idea. You know that smell when you get clothes from the dry cleaner. Well, that's the smell of you being exposed to cancer-causing chemicals. So I tell people, think about what you're doing. And I tell people, you know, hang the clothes maybe in a bathroom. Take the bag off, let those vapors come off of the clothes. Turn the fan on, you know, go in the bathroom, turn the fan on for a few minutes to replace the air, at least for the first day or two, so that you're not exposing yourself to whatever chemical they've used to treat those clothes. Same thing in the car, you know, don't take the bag off and then put the clothes in the car, because you're in an enclosed space. It may not be for very long, but the car may not have a good air exchange, and you may be exposing yourself. So a lot of dry cleaners are now moving towards non-chlorinated solvents. That is a very good thing. In New York State, you know, they refer to themselves as organic dry cleaners. That can be misleading. You know, we're dealing with organic chemicals, you know, these solvents. So, you know, if you have clothes dry cleaned, and, you know, when we're all done with COVID, maybe we're going to wear nice clothes again, and, you know, ask your dry cleaner, you know, what chemicals are you using? Are you using non-chlorinated solvents to treat your clothes? So I talked about mitigation systems. This is what we do if we find a problem. The figure on the left is a schematic. We'll drill a hole through the basement slab. We will tie into the gravel bedding. You know, typically when they build a house and pour a basement slab, they'll have a nice gravel bed underneath, mostly for structural stability, so the slab doesn't crack and break. But that also makes a very nice transmission pathway for vapors that collect. We tap into that. We put a stick up a riser. We'll stick a fan in the attic. And all we're doing is giving these vapors a path of lower resistance, that instead of coming up through cracks in the slab or a sump, we've got an easier path for those vapors to travel so they don't enter the house. This is a pretty low powered fan. All it has to do is create enough differential pressure to be greater than whatever is going on inside the house that may draw the vapors in. And then the picture on the right, this is a little different. Instead of putting the fan in the attic, these guys have put the fan on the outside of the house. I'm guessing this is in a warmer climate, because I would have a concern with condensation. On a cold day, you're pulling humid air from beneath the slab, and you have a potential for condensation to form right at this elbow that could freeze and that could block the pipe. So I'm guessing this is a warmer climate, but the design is essentially the same. For larger structures, this is a warehouse. If we have to retrofit, we'll actually saw cut the slab. We'll put perforated pipe in beneath the slab, backfill it, replace the concrete, and then vent the whole system out to an outside vent. And then for new construction, it's a lot easier. This is some kind of a warehouse. We'll put the perforated pipe in. We'll put gravel around it, pour the slab on top, and then have some kind, I don't know if this is a manifold of some kind. I don't know if the fan will tap into this structure or if it'll be drawn outside. But again, the purpose is to just prevent those vapors from accumulating within the building. So now we'll talk about groundwater migration and how geology is a really important factor for how those contaminants migrate. In this division, we've got about 300 employees statewide. About a quarter of them are geologists. We rely on them heavily to help understand what's going on in the subsurface, help predict what's going on, because that helps us, find these contaminants. And you'll see in a minute how the geology actually affects how we clean up these contaminants. So what you're seeing here is a cross-section of the ground beneath a particular site. We've got fill is this top layer. We've got a little bit of a sandy matrix, which is the second layer. We've got sort of a silty, maybe a sandy silt, which is this third layer. And then we've got a dense clay till down at the bottom before you get to bedrock, which is the lower gray layer. You may not be able to see the concentrations. These are in blue are the concentrations in water. In brown are the concentrations in soil. And what you'll see is the highest concentration in water is in this well right here. Also, this is a pretty high level. This one is pretty high. But then when you get down to here, these concentrations are much lower. So what's happened is the solvent has followed the topography, gotten through that sandy layer, which is pretty porous and permeable. It's followed the contour of this sort of semi-permeable layer. A little bit has gotten into this well just below the interface here, but not much has gotten down to the bottom. If I were to look for pure product and pure solvent, I would be looking right in this bowl. And we see this topography much more dramatically in some locations. You'll actually see fairly deep depressions where we actually get pools of solvents that have formed. If this was a clay, I would be looking for something, or I'm sorry, a sand, I would be looking for pooling, down in this layer as well, which is a little more dramatic. So geology plays an important role in how these contaminants migrate, and it also plays an important role in the remediation options that we have available to us, which I'm going to show you. So when we talk about the toolbox, of remedial options that are available to us, we've got a couple things to select from, and the site conditions dictate what tools in the toolbox that we use. One of the easiest ways to get rid of soil contamination is to demolish the dry cleaner if it's no longer being used, and then dig out the soil beneath it. This is a dry cleaner in a small city, again, outside of Albany, where we were able to demolish the structure. It was a little tricky because we had houses on either side. We put vibration monitors on the structures with alarms, and if there's unacceptable vibrations during the activity, we'll stop and see how we can do it better. I swear that this fascia was missing before we started. We didn't do this, but we do conduct pre-demolition surveys of adjacent structures for exactly this reason. We don't want to be sued by this owner because, something settled on his house, or because something, or a pre-existing condition he wants us to make him good for. So we can excavate these properties. Once we're done excavating them, this is not the same property, but this was another project in New York City. We will excavate the contamination out of them. And what you're seeing here is a temporary fabric structure that we use to conduct these excavations in. And it's a lousy picture, I'm sorry, but it shows that the shoring that we need to put up in order to safely dig this without causing a collapse. These are sheet piles that are braced here on the corner. You can see a brace right in the foreground here. This excavation went about 30 feet deep. These sheets were probably installed about 50 feet deep. So we use geotechnical engineers to design these systems so that we don't have collapses as we're doing them. We have to be very careful about indoor air quality because this is an enclosed structure. The equipment that's inside, burns fossil fuels, so carbon monoxide is a big consideration we have to monitor. We actually put monitors right where the operators are on the facility or on the equipment. And then we have to design a certain number of air exchanges per hour. That air is treated if there's solvent or any other petroleum that we're digging out. We have to design systems to remove that before it's discharged to the atmosphere. So air exchange, air quality is a big issue when we do these indoor excavations, as well as stability. And then I show this picture. This is obviously an outdoor excavation. There were no structures nearby, so we were able to do this without shoring and without putting it in an enclosure. It demonstrates that we have to deal with groundwater. This is typically contaminated groundwater, so we pump it out and we treat it. But I show this, and if I had a live audience, I would ask, does anybody see anything wrong with this picture from a safety point of view? And that is the fact that we have a loaded cement mixer. I think they're pouring the footings for a new structure. This to me looks like a soilcrete wall. I think the structure that was being built here was going to have underground parking. But you have this loaded dump truck right next to an open excavation where stuff is sloughing in. This to me is a red flag for a structural failure. So anyway, they made it out without the cement truck collapsing into the hole, but I think that's why this picture was taken, was an example of a health and safety problem. So what do we do with the soil when we're done? This is a cartoon from one of our vendors for a thermal treatment unit. They bring the soil in, they load it into a screener. The oversized material is screened out, typically is not contaminated because the contamination sticks to the fines. We then run the soil through this rotary kiln, which is run at about 1,000 degrees. That temperature is enough to vaporize all the contaminants from the soil. The soil passes through from left to right, comes out this conveyor as a nice, very dry but clean soil that can be used for a backfill somewhere. The vapors are then routed into this afterburner, and they pump up the temperature to about 1,400 degrees. And that is hot enough to destroy even a chlorinated solvent. These are used a lot with petroleum contamination because the petroleum actually has a fuel value and you don't have to bring as much fuel in to run this equipment. The petroleum also strips out at a lower temperature. You don't have to go quite as high. So this is one of our go-to technologies for treating soil. So toolbox 2, groundwater extraction and treatment. This is that Grumman plume that I showed you earlier. This is the conceptual plan for treating that 4¼ mile long groundwater plume that's affected public water supplies. Each of these icons is an extraction well and a very high capacity extraction well. It's connected by a network, or it will be connected by a network of piping to 2 centralized treatment plants that are going to treat enough water probably to serve a small city. These are going to be huge plants. One of them is going to be discharged to the state park. This is a golf course, and the golf course can use the water for irrigation. So that's kind of a win-win. It's kind of a green solution to getting rid of the water. The technical challenge is as much how to get the water out as it is what to do with the water when you're done. And then this treatment plant will discharge to a local creek. The pumping of this groundwater is going to be so high that it actually is going to affect the water table, which has the potential to dry up this creek, which happens to be a trout stream. So the treated water will be discharged to the stream in order to maintain the water levels. So, you know, one of the options, this water will be drinkable quality. Um, One of the options that has been discussed is actually putting it in the distribution system. But the perception of people drinking treated contaminated water is not very good. We would be at risk if something happened in the treatment plants that for a period of time the treatment wasn't fully effective. And so the decision was made not to put this into the water systems. So this remedy is going to cost Grumman and the Navy over $500 million. This is a $500 million remedy. They're going to have to operate it for at least 30 years, probably longer. So this is a significant financial commitment and financial responsibility from 50 years of discharging solvents to the groundwater. So this was an interesting technology that's been developed probably over the last 20 to 25 years. And it relies on the vapor pressure of these solvents. And what this involves is blowing compressed air into the groundwater, essentially bubbling with very small bubbles into the groundwater, vaporizing the contaminants out of the groundwater, and then collecting the vapor in the unsaturated zone that's above the groundwater table. This is called air sparging, which is that bubbling operation, and vapor extraction, which not only collects the vapors that come out of the groundwater, but also any vapors that might be collecting in that unsaturated zone. This works very well in coarse geology, that sand and gravel aquifer, because of the pore spaces in between the sand and gravel, allows air to move efficiently through it. We typically will conduct a pilot test of the vapor extraction so that we get the spacing of these wells right. You know, there's a certain radius of influence that the extraction has. And so we'll design these wells so that there's a good overlap and so that we thoroughly extract all the vapors that might be present and that might be generated from what's being bubbled in the groundwater table. So this works well for small releases that haven't traveled 4¼ miles or haven't gone too deep. You can imagine as you get 100 feet of water column, the air pressure needed to bubble air through 100 feet of water column is just excessive. You'd need massive compressors in order to run this. But for relatively small and shallow problems, this technology works really well. So here's a picture of what it looks like. These are two different systems, actually three different systems, but we can mount this technology inside of a trailer, and so it's mobile. You can move it from site to site. On the lower right-hand corner, these are the air compressors for what's being bubbled through the water column. This is the blower for the air that's being extracted from the subsurface. You see the hoses that come out that are connected to a series of hoses that travel out to the various injection wells. And then here's a sort of a different system with different types of hoses, but these are the wells with the stick-ups, and then you see that the compressed air is being injected into them. Again, it works really well, allows us to treat the contamination in place without having to extract it, through a big pump and treat system. For sites that we cannot excavate, that allows us to get the vapors and the soil contamination out of the ground without having to destroy buildings. So works really well. A similar technology is in situ thermal treatment, where we inject heat of some kind into the ground, including below the water table. It vaporizes the contaminants, and then those vapors are collected in these extraction wells. And this works really well in clayey soils because the clays and the silts are very good at transmitting heat. Uh, so where the previous technology was good for sand and gravels, this is good for tighter soils. And that heat can be injected either in the form of electrodes, and you need a significant power source in order to heat up not only soil, but also some groundwater. Or it can be in the form of steam. And I think the facility that you see on the right-hand side is a steam um, operated thermal treatment system. And I say that because of these knockout drums for the water vapor that's collected that comes out of the steam. These are the carbon treatment units that treat the vapors that are coming out of the soil. And I think what you're seeing here is a steam generation plant, again, built on a trailer. You see an insulated pipe that's going out, and then the steam is distributed to all these injection points throughout the treatment area. So um, again, a very handy technology for treating contamination in place. This happens to be an open field, so you know, maybe we could have excavated, though I'm not sure about depth and everything else. So the most interesting technology maybe is something that was sort of discovered by accident. And as we were investigating these sites, say it was a PERC site, a perchlorinated ethylene site that was fully saturated with chlorine, as we installed wells and took samples further away from the site to track the spread, we were seeing more trichloroethylene, where one of the chlorine atoms had been stripped off and replaced by a hydrogen atom. We knew that this chemical was not present in the original release. And so something was happening that was removing the chlorine and replacing it with hydrogen. And as we move further out from the source area, we see more and more hydrogens replacing the chlorine. Here, they're being replaced in the molecule across from each other, here next to each other on different carbons, and here being replaced on the same carbon. These are all, you know, dichloroethylene in various isomer formations. As we moved further away, we would see 3 of the 4 chlorines being stripped off. And in some rare cases, we would actually see all of the chlorines being stripped off and replaced with ethylene, which is a fairly innocuous chemical without chlorine in it. Ethylene is what's used in blow torches, and people use it all the time without, you know, significant health problems. But the interesting thing was that this was only happening in certain circumstances. It was not happening everywhere. In many cases, we would see just the parent compound. We would see maybe one of the daughter compounds, as they're called. And either there was no degradation happening in the environment, or there was just minimal degradation and it was not being fully transmitted all the way to the end and full dechlorination. And so as we studied this more and more, we found that there is a soil microbe that was responsible for this. And it actually got the name dihalococoides, meaning it dehalogenates compounds, and ethenogenesis, which means it creates ethene. So the scientists discovered this as part of our investigations, and they named it. It had never been discovered before, and realized that it is responsible for, in some cases, dechlorination of these compounds. And the more they studied it, they realized that this is an anaerobic bacteria. That is, it thrives in the absence of oxygen. And the circumstances in which it did not do well were circumstances where there was a lot of oxygen in the aquifer. And the circumstances where it did well was where, for some reason, all of the oxygen had been removed from the aquifer. And in many cases, it's because other contaminants were present in the aquifer, and bacteria that eat those contaminants and that use oxygen used up all the oxygen. Those bacteria went dormant, and then these bacteria began to thrive and start working on the chlorinated compounds. So that spawned a whole new technology called enhanced bioremediation. And we've studied the conditions that we can optimize these naturally occurring soil bacteria to fully or more fully degrade these contaminants. And what it involves is somehow creating anoxic conditions in the aquifer and getting rid of all the oxygen. And then B, what nutrients do these bacteria need to, really become fully effective? And the interesting thing is to make the aquifers anoxic, we would inject things like molasses or whey, the byproduct of cheese making, because those are known, and they're relatively innocuous. Those are known to be eaten by soil bacteria and use up the oxygen and allow these anaerobic bacteria to do their jobs. So what you see here is, this is called biostimulation or bioaugmentation. Nutrients are injected into the plume. We allow the bacteria to work as the contaminants travel through the aquifer. In this example, they add more nutrients and even some microbes back into the aquifer to sort of finish the job as the groundwater moves. So this is sort of a neat technology. It's not good for high concentrations of contaminants, but it works really well where there's low concentrations of contaminants. So what we typically do is, we'll do something in the source area, something more aggressive, and you'll see that in a minute, including excavation, including pumping and treating. And then to sort of deal with the low level stuff that's left over, we'll use this enhanced bioremediation. So the last tool in the toolbox, and there are many more, but these are sort of the primary ones, is actual chemical oxidation. And this is the injection of chemicals that are so strong that they actually rip the chlorinated solvent molecules apart. And the most typically used compound is potassium permanganate. There's been some peroxide. Persulfate is a relatively new oxidant. The advantage of persulfate is that you can make it heavy so that you can inject it with a density that's greater than water, and it will actually follow the contaminant down and sort of treat it as it goes. And then ozone, we will actually sparge. Ozone is a gas at standard temperature and pressure. So we will create ozone, inject it, and that can break down these chemicals. So in this figure, it's actually showing some kind of a barrier that's installed. Maybe this is a trench or a slurry that's injected into the ground to create sort of a wall of treatment medium. We can do this with wells as well. But if I were doing this, I would probably do it closer to here, closer to the source area. I think this cartoon is just kind of shown for an example. But in situ chemical oxidation is a very useful technology. One of the problems is as you oxidize the soil minerals, it can actually create complexes that plug the aquifer. And you can get fouling of your trench. So this is not necessarily good for all aquifers, but because of that, but where it's good, it's useful. So we have these tools in the toolbox, and just to summarize, the ones we select depend on, you know, how much contaminant is out there, how deep it is, how widespread it is. The geology is a big influence. Any infrastructure constraints that we can't excavate around, the presence of other contaminants. In that oxidation, that chemox example, there are some contaminants that if you oxidize them, they actually become more toxic. Things like chromium, arsenic are some of those that, so if, depending on the other contaminants, we don't oxidize. And then of course costs. Everyone's got their eye on the bottom line. We look at life cycle costs. Some of these systems you need to operate for several years. Whereas if we can excavate and go right at it, even if you have to knock a small building down, it may actually be cheaper to do that and be done with it. So all factors in what we select from the toolbox. So now's the second half of the discussion, and that is these new fluorinated compounds that have emerged as a problem in the last roughly 5 years. When you look at the research and the products that are out there, there's roughly 5,000 compounds that are made with some kind of combination of carbon and fluorine, the so-called fluorocarbons. Most of the major products are these firefighting foams, anything that is stain and water repellent. So, you know, your Scotchgard treatment of your couch and your clothes, your Gore-Tex, that's what makes water bead off and not leak through your Gore-Tex coat. Anything that is non-stick is typically made with a fluorocarbon. Teflon, the waxes, including the waxes on my skis that I use. Food packaging, and we'll look at that in a minute. Cosmetics, they're finding it in a lot of cosmetics. It is very useful as an industrial product. And then, of course, anything that we make, we end up throwing away. And so landfills have emerged as a significant source of these compounds. So another chemistry slide. We were dealing with chlorine in the past discussion. We're now dealing with fluorine. They're members of the same family. And we're talking about the bonds that hold carbon to chlorine or carbon to fluorine. The carbon to fluorine bond has been described as one of the strongest in all of organic chemistry. One of the reasons is that fluorine is a relatively small molecule, and it holds its electronegativity very tightly to whatever it bonds to. To break apart the carbon to chlorine bond is about 400 kilojoules per mole. To break the carbon to fluorine bond is much higher. And that becomes a problem for us when we talk about how to destroy these contaminants once they're released. So just a little chemistry background. Here's some researchers' analysis of where PFAS, these perfluorinated alkyl substances, are found in typical consumer products. Firefighting foams and textiles being the heavy hitters. But again, food packaging, anything stain resistant, typically is made with a fluorocarbon. Abby wanted me to show this. I pulled this one off of WebMD. This is a few years old now, but when they sampled things like dessert bread wrappers, they found PFAS in 56% of what they sampled. Burger wrappers, roughly 40%, paper boards, 20%, and fortunately our paper cups are PFAS free. But you know, they're in pizza boxes, they're in microwavable popcorn bags, they're in our pet food bags, you know, anything you don't want something to stick to or water to leak from, they are typically, they're typically using these PFAS materials. It's interesting when you look at sort of the other uses of this stuff. When we go out and sample a site for PFAS, this is the checklist that we use to make sure that we're not introducing PFAS from what we wear and the equipment we use into the samples that we collect. And I think this is instructive because it shows you the universe of where this stuff is used. You know, Gore-Tex, as I mentioned before, Tyvek, which is our go-to, you know, the white suits that you see people in, you know, had been our go-to when we take samples or clean up sites. Cosmetics, moisturizers, hand cream, sunscreen or insect repellent. There are certain brands that are tested as PFAS free, but for the most part, these chemicals are in sunscreens and insect repellents. No waterproof field books, you know, the survey books that a lot of us use. No plastic clipboards, no Post-it notes because it's in the adhesives, no blue ice packs for the coolers that we put the samples in. So I think this gives you an idea, and you probably are seeing a lot of these products in your own life that likely have PFAS in them. So I'm going to talk about one group of those chemicals, and that's firefighting foams. You know, a lot of my experience in investigating one of the sites you'll see later is involving firefighting foam. You can imagine that a fire on a ship is a serious concern. And the Navy lost an aircraft carrier back in the 60s. Aircraft carriers are particularly susceptible because of all the jet fuel that they're handling and storing. And they're fueling up on the decks, and jets are taken off with flames shooting out the back. So the Navy really needed a very effective foam for dealing with particularly aircraft carrier fires. They had some early protein-based foams. The problem was that they broke down under heat. They didn't mix well with seawater, and they often broke down when exposed to the jet fuel that was burning. So the scientists at 3M said, let's explore this very tight carbon to fluorine bond, and let's make a product that the Navy can use to deal with these situations. This ChemGuard is actually not a foam, but this is the only picture I had from a site that I had worked on. But, and this material turned out to be extremely effective. It made a blanket over the fire. It suppressed the vapors that would cause the fire to spread. It could be mixed very easily with seawater and deployed in these automatic foaming systems that you see on this aircraft carrier. That in an instant, if there was a fire on board, you could trip, you know, a sensor, you could hit an alarm. The foam concentrate was stored under pressure. You could pump seawater, mix it at 3%, and deploy a very effective system for putting that fire out and preventing further spread. Here's a closer look at the bucket, the foam concentrate. Hydrocarbons like jet fuel, you mix at a 3%. Alcohols, which are a particular problem, and I'll talk about those in a minute. You got to mix at a higher proportion because alcohols are polar. They will actually dissolve the bond of the foam concentrate to water and can weaken the effectiveness of the foam. So, but again, it only takes 3 to 6% of this foam concentrate to mix with water, and you have a very effective foam for dealing with fires. So it was first deployed by the Navy on ships. It then became sort of the standard practice for any place jet fuel was stored, including aircraft hangars. And what you see here is a test of a foam suppression system in a hangar. Again, you've got municipal water or a water supply under pressure. You've got foam being stored in a tank under pressure. A sensor goes off, you mix the two together, and you have this high expanding foam that can snuff out a fire, in an instant. But like any mechanical system, they are prone to failures. A sensor can go off improperly. Um, Gaskets can leak. Valves can be improperly turned. Um, and what you see here is a system that was a foam that was released in a hangar while the jets were still in it. This is not something that the Air Force likes to do. Um, I had a case on one of the sites I worked on where someone opened the wrong valve and the concentrate in the tank actually backwashed into the water supply. Um, and the people complained about the taste. And so what did they do? Well, they flushed the water supply out and just release the stuff until the water tasted good. And I'll show you the effects of that later on. So, and then what do you do if it's released in a hangar? Well, you get out your fire hose and you wash it out of the hangar and down the street. Some poor guy, forgot to move his car, and he's got this stuff, all over his car. And of course, this washes down into the nearest water body. So, again, system failures. And then this material was so effective that firefighters would carry this on their trucks in small buckets. What you see here is a fire training facility where they, this is probably like an open elevated pan where they put some kind of a flammable material in it, lit it on fire, and then the firemen are training with their foam cannons to put the fire out. In New York, nearly every county has a fire training facility, and nearly every county released firefighting foam as part of their flammable liquids training. You see the foam on the ground. Again, before people knew it was bad stuff, the stuff would just be open to rainwater. It would get washed out and follow its way to the nearest water body. So New York is particularly concerned with all of these county fire training centers where the local fire departments would come, the volunteer fire departments, and train with their foam cannons. So here's just a picture of a foam trailer. If you have a gasoline tanker that rolls over, you need to get out there quickly with one of these to put the fire out. And even if it doesn't catch fire, they would typically spray this as a precautionary measure so that any spark, would not catch the gasoline vapors on fire. And the reason in New York, especially, these foam trailers are so important is because we move a lot of flammable liquids around by rail. I don't know if that's the case in Indiana. Remember I said alcohols are a concern? Well, we blend ethanol into our gasoline at 10%. That ethanol is produced in the Midwest, in the Corn Belt, and then shipped to the refineries all over the country, including, here in New York, and it's blended into the fuel. So we ship a lot of alcohol by rail, and the local fire companies need to be prepared with a rig like this in case one of those tankers derails and there's ever a fire. So, and then of course the firemen need to train with that equipment, and that's what you're seeing. The irony here is not only is he spraying foam, but he's wearing materials that are water resistant, that are chemical resistant, and they're finding that a lot of these suits were also made with PFAS. So, and then of course, when the firemen were training, it became a local event. And this is a small town in Western New York. This guy is very proudly wearing his hazmat suit as he's practicing with his equipment. When firefighters are responding to a a tanker or a truck on fire, or a car on fire, they need to be ready. And these guys need to train and know that their equipment is going to work without having to fiddle around with it at the scene of a fire. So the training is very important. These guys weren't doing anything bad because nobody knew the foam was bad at the time. But this became a small town event. This guy's taking a picture. He's standing just outside the splash zone of the fire. Here's another picture of the same training event. He's shooting his water cannon or his foam cannon. The problem is, you can tell by the topography that this is at the top of a hill. The village's water supply well is at the bottom of the hill. And so this stuff washed off, followed the drainage down to the bottom of the hill, infiltrated into groundwater, and contaminated their well. And we found this out. New York State has a new law that all water supplies have to test for these chemicals. These guys tested back in December, got the results back, and we had to scramble to find these guys another water supply. We provided bottled water to them for a week or so. We found them a new supply well that could very quickly be brought online. That was outside. It was actually on the other side of this little ridge. And they were very fortunate that they had another water supply sort of standing by. Otherwise, we would have been delivering bottled water for months and months to these people. So, and I think we're going to find this more and more as we investigate these fire training centers. So what are these chemicals? The most studied ones are the so-called C8 compounds that have 8 carbons, shown here on this chain. These are fully saturated with fluorine on 7 of them. They have different functional groups on the end. This is a carboxylic acid. This is a sulfonate group that give them the different chemical properties that make them useful. This one is used in the manufacture of Teflon and textiles, PFOA. This is the one that they use for firefighting foams, PFOS. But they're basically sister compounds, 8 carbons, fully saturated with fluorine. And these are only 2, and these are the 2 most studied for the reasons I'll show you in a minute. But like I said, there's 5,000 of these in various configurations that, quite frankly, nobody knows a whole lot about. So what are the health effects? Well, one of the problems with these is that once they enter the body, they spend a long time in the body. They are not easily flushed out. They cause liver, testicular, and kidney cancer, low infant birth weights. They disrupt the immune system. They increase your cholesterol, and they affect your thyroid. And then who knows what other impacts these are, because these really are only recently studied. So the reason we know as much as we do about these compounds is because of the very famous C8 study that came out of the DuPont Teflon plant, not too far from you guys, in Parkersburg, West Virginia, right along the Ohio River, right on the border between Ohio and West Virginia. They had a plant that manufactured Teflon for nonstick cookware. They discharged not only the PFOA, but other fluorinateds through their stack, discharged it to the river. It entered several water supplies. And I'll show you the implications of that. They've been doing that since the 1950s. Only recently, up until 2013, they did health studies on the residents who were drinking from these water supplies or who were exposed through airborne emissions. And they got over 69,000 volunteers to have their blood sampled to find out how much was in their blood, to do medical histories, to find out what various cancers and other health effects they had. And that was reportedly the largest human study of a correlation between exposure and health effects ever conducted on Earth. And it was good enough to establish a probable link between those exposures and the health effects. But, it took 8 years to do those health studies. This is not quick science. It takes a long time for those health effects to come around, to be created. And if you're interested, there was a movie made in 2019, Dark Waters. This is the history of primarily the legal case against DuPont. Um, I found it fascinating. It is focused on Teflon and the workers who were exposed on the production lines. There's one scene in the movie where DuPont wants to investigate the health effects on the workers. They actually put this material in cigarettes and gave the cigarettes to their workers, and then studied whether there were any health effects from that route of exposure. A story that they took all the women, especially pregnant women, off the production line. And then when people became suspicious why they did that, they put them all back on the production line. And there's themes of taking on a corporation in a company town. The backlash against the workers who joined the lawsuit against DuPont because Parkersburg is a company town. A very interesting movie, I found. I found it on Redbox. I think it's on Amazon pay-per-view, but certainly Redbox has it. Anyway, so as I said, these are relatively new compounds. Many states do not regulate these compounds. You'll recognize Indiana and New York as two states that do. This first column, which is the yellow, this is a drinking water standard, also called an MCL. I think we're fortunate that our states now have a drinking water standard for these compounds. 3M, as I said, was an early producer of PFAS. Minnesota is pretty far ahead because they've been dealing with this for several years. North Carolina, 3M or DuPont, I think, actually has a plant in North Carolina. So the states where you see that they have standards are primarily the states where the companies had production plants, and the problems started to become evident. Michigan, I guess, is ahead of everybody else. I think there was another producer up in Michigan as well. So this is the airport and the Air National Guard base I've been dealing with down in Newburgh. This is a city of 29,000 people. And this is, an airfield that is both a commercial airfield as well as an Air National Guard base. But I think this is typical of a lot of airports around the country. So they had an accident in one of their hangars. They lost 4,000 gallons of foam concentrate. This is the city of Newburgh's drinking water reservoir on the right-hand side. There's a watershed divide between that lake and another lake, which is another water supply for another community. So everything on the left, everything on the left goes to Beaver Dam Lake. Everything on the right of the orange line goes to Lake Washington. They had a plane catching on fire back in 1996. They pulled it off onto the median. They sprayed the heck out of it with foam. And so we see ongoing discharges from that area, through the surface waters and down into that lake. They have a training area where, by FAA rules, they have to test their equipment out so they're ready to fight fires should they happen. So we have an area where they spray about 3 gallons of foam concentrate every year to test their equipment. That runs down we have these old releases of 4,000 gallons of foam, and that's all contributed to contaminating the city's water supply. So, you know, how much PFAS does it take to contaminate a lake? New York's drinking water standard is 10 parts per trillion. That is about, you know, the analogy of one drop in 2 Olympic-sized swimming pools. It's about 10 seconds in 31,500 years. It takes an infinitely small amount of contamination to potentially cause a health effect. So in that lake, the average concentration is 2 parts per trillion, which is 20 times the drinking water standard. The lake is about 2 billion gallons in size. When you do the math, how much foam did it take to contaminate that lake? And it's only about 3.5 pounds. So less than half a gallon of those 4,000 gallons that were released have made its way to the lake and created this problem. And so there is a bunch load of foam still out there that threatens that particular lake. So the toolbox of treatment technologies for PFAS is nowhere near what it is for the chlorinated compounds. Activated carbon works really well. We use carbon on all of the impacted water supplies, and I'll show you some pictures of that in a minute. One of the emerging technologies is actually to take powdered activated carbon, put it in a slurry, and pump it into the ground. And that's just to sort of bind up the carbon or the PFAS as it moves through the aquifer. Excavation and landfilling, a lot of landfills will no longer accept it because this stuff passes through their treatment. Thermal treatment is a big question mark. We don't know enough about how this stuff behaves, how hot you have to make it to break apart that carbon to fluorine bond, the residence time in that rotary kiln to thoroughly destroy the chemicals. And if you don't thoroughly destroy it, what are the products of incomplete combustion? You know, in the chlorine analogy, if you don't heat the molecules up for long enough and hot enough, you create dioxin, which is one of the most potent cancer-causing chemicals on Earth. And so we're very careful about how we handle chlorinated compounds. And we're very concerned about an analogy with fluorine, that if we don't heat the soil up for long enough and hot enough, that it could create a dioxin-like compound that's even more toxic. So a lot of questions about thermal treatment. So very quickly, these are carbon treatment systems. This is the system for the city of Newburgh, 29,000 people. Just to give you a little bit of scale, that's a guy standing on a man lift. You know, there's a porta potty. The way you build these things is you bring the canisters in and you set them up, and then you build the building around it because, you know, they're so big and so difficult to manage inside a building. And everything from that to a basement-sized system for an individual house. These are 5-foot canisters filled with carbon. We connect it to the well pump. Carbon can be a medium for biological activity, particularly in a homeowner well. So we put a UV light on these systems after it passes through the carbon to absorb all the contaminants. The UV light kills whatever bacteria might grow on that filter before the water enters the house. So that's typically the systems that we build either on a city scale or a homeowner scale. This is a schematic of the city size system. I'm not going to spend a whole lot of time going through it. You know, we have individual vessels, we have pairs of vessels, and we have a whole train of vessels. And the key thing here is that we have to monitor for breakthrough. Water typically flows from the bottom of the canister, the contactor, up to the top. The carbon along the way absorbs all the contaminants, but at some point becomes saturated and those contaminants start to break through. So the operation of these systems is as important as the design. we have to monitor the breakthrough. So by the time you get to the end of one of these trains, you don't have carbon or you don't have PFAS breaking through the system. And then we can open up the tops of the vessels. We suck all the spent carbon out and then replace it with fresh carbon. And that's how we operate these systems. So they do have a significant operational cost, and it requires some vigilance to continue to monitor. So the key engineering parameters for those that are interested in the engineering details, the contact time of the water with the carbon, as you can imagine, is the key parameter. You know, we need enough time for all of the contaminant to pass out of the water phase and into the carbon. The flow rate will determine the total volume of the vessels, and then different contaminants have different absorption rates. PFAS, fortunately, is a pretty sticky molecule. It sticks pretty well. A lot of the smaller molecules do not absorb as well. They need more contact time. So, and in fact, some contaminants are so small that they pass right through and they don't absorb to carbon. So, again, the breakthrough volume is something we have to monitor as we operate these systems. How much volume can you put through before the contaminants start to break through? Some of the standard engineering considerations are the pressure drop, you know, that affects the size of the pumps that we need to overcome the pressure drop. The particle size is a trade-off. You know, a smaller particle size will absorb more contaminants, but you have a greater pressure drop. So we play those against each other. And then typically what you do is you take a jug of the contaminant that you want to take out of the system, you send it to Calgon or American Carbon or one of the other vendors, and they'll do a pilot test and they'll help you scale up your full-scale design. So key research needs, as I said, you know, there's so many of the compound out there. We're never going to know all the health effects. You know, it's taken so long just to determine the health effects of 2 of them. So really, the key question is, what is the safe level for the most common PFAS that we see out there? There's about a dozen of them that we see time and time again that are most commonly encountered. We are still learning about their environmental behavior. We have not seen the defluorination that we saw with the chlorinated compounds, so we don't think there's any bacteria that work on them. But they do behave differently. They don't stick to clays as much as some of the other contaminants. So as I say, we're still learning. And then ideally, we would come up with some in situ treatment technologies so we don't have to pump this stuff out of the ground and treat it with carbon. So, you know, for you, the young engineers out there, if you're interested in the chemistry of contaminants, boy, this is a huge research need, how we can treat these contaminants in place. So that's it for me. I'm happy to answer any questions.
Anybody have any questions? All right, well, thank you very much, George. We did record this, so if anybody wants to kind of circle back or have any coworkers or friends or family that would be interested, we're going to be posting this up on our website. I also want to let you guys know about some events coming up. So to close out Engineers Week, we are having a movie night next Friday. So we're going to be watching Code Girls, and then we're also going to be having some trivia about African-American women in STEM. So we'd love to have you guys there. It's going to be at 7 p.m. You can sign up on the Eventbrite. That's also going to be a free event. Sounds like Olivia's got a question.
Hi, yes, thanks, Abby. I have a couple of questions. Can you hear me okay?
Yep.
Oh, great. Okay. I am curious if there are any concentrations of chlorinated solvents in Indiana. And I was curious what types of cancer are most prevalent. I know you said that it deposits in the liver and the kidneys, but I was curious if there was a type of cancer that it presents itself as most.
Yeah. On the Indianapolis question, your water supplier is required to tests for these compounds and to keep records of these compounds. So I would direct you to your water supplier. I'm sure you can Google it and find out, Indianapolis water supply, and you can get a contact. They may actually post their reports online. I know that a lot of ours do. So as far as the cancer, I think the most common cancer is kidney cancer. For the PFOA site we had in Hoosick Falls, that became apparent when the residents came down with kidney cancer. So that's probably the top one.
Okay, thank you, and thanks for all the information.
You're welcome.
And Olivia, I do know there's a website, I think it's called What's in My Water. And you can look up, I think nationwide, what water supply you're hooked up to, and you can look up specifically what's in your water. So I know I've done that for Indianapolis specifically, and I can share that with you. I'll send it out with a follow-up email. And it looks like Sam also has a question.
Hello, I'm Sam Granger from over in the UK, a company called Soccertech. Over in the UK, the PFAS standards are a lot less stringent than they are in the States. So I was just wondering, what sort of cross-contamination issues are you having, and how sort of significant are they? I know you mentioned sort of field clothing and field equipment that can't be used Teflon, those sort of materials. Thank you.
Yeah, I did not hear the whole question. Abby, can you?
Yeah, we're having, Sam, could you turn maybe your volume up or speak close to your phone or the computer possibly?
Basically, how significant is the cross-contamination of sort of field equipment and field clothing to the chemical results, essentially?
Yes. The question was how significant is cross-contamination from field equipment or clothing? We have had cases where, our detection limits are down at the 2 part per trillion level. And so it doesn't take much to cross-contaminate a sample. We had a case where blue ice was used in the cooler, and it actually created a 20 part per trillion false positive in a blank. When we take samples, what we typically do is we have a sample of water that's certified clean that comes from the laboratory that's shipped with the sample bottles. We open it in the field. We sometimes will pour it into a stainless steel sampling device that we're using, and then pour it back into the sample vial just to see if our sampling methodology is somehow introducing the contaminant. And sure enough, we had a case where we had levels that exceeded the drinking water standard in our blank sample. And so that told us that something was done wrong in the field, and we had to go back and resample and take all new samples because our blank was contaminated.
Excellent. Thank you very much.
Sure.
I have 2 questions. First one is, how do you find room for wells and treatment plants, particularly thinking about that Long Island sample, because it's basically a giant, highly developed suburb? And the second question is, where does chlorine go when it's stripped by the bacteria?
Good question. So yeah, it's not only the wells in that case, but also the pipelines. And we actually are seeing more problems with getting the pipelines sited than the wells themselves. The municipalities typically have rights of way, and we can strategically place wells either in publicly owned or areas with public easements, as long as that matches up with where we need to strategically place them to achieve the design goal of extracting the groundwater. And similarly with the easements for utilities, but it does require the cooperation of the municipalities. Fortunately, most of those municipalities have had their water supplies affected by the plume, and therefore they're pretty motivated to cooperate with us. So we will lay the utilities for to transmit the water to the treatment plants alongside the other publicly owned utilities such as either gas or water lines or sewer lines as much as we can. We do, however, secure easements on private properties, where we absolutely need some infrastructure on a privately owned property. In this case, Grumman may have to reimburse the property owner or somehow convince the property owner to grant an easement to place a well or to place a lateral. Second question, where does the chlorine go? Typically, what we call full mineralization occurs, and it will either become HCl, hydrochloric acid, at very, very low concentrations in the aquifer. Remember, we're dealing with part per billion or part per trillion levels, and so any acidification that is caused by the creation of HCl is not enough to affect an aquifer. We do see it coming out as chlorine ion, and if there's any sodium or manganese in the aquifer, it will preferentially convert to sodium chloride or magnesium chloride. That's typically what happens to the chlorine.
Excellent. Thank you.
Yep.
Any more questions? Okay. So yeah, again, just a reminder that we've got the movie night coming up next Friday at 7. And then we've also got a professional development event coming up on March 2nd. And that's going to be in partnership with Women's Transportation Seminar. We've got a speaker, Carla Miller, who's going to be talking about shifting to win, taking busy professionals from stress to success. And that's going to be from 11 to 1. 11:30 to 1. So be on the lookout. We're going to be sending out a link to sign up for that. And then if you guys have any follow-up questions, we'll send out George's email and you can follow up with email with him if you think of anything. But other than that, thank you so much for joining us. Thank you, George. This is a very helpful presentation. I hope everyone learned something.
Thank you. Bye.
All right. Have a good Friday, everybody. We'll see you next time.
Thank you.
Thank you.